Right now, somewhere in the world, a droplet of tin is falling. It falls through a sealed chamber. There is no air inside. It is 30 millionths of a meter across. This happens 50,000 times a second, right now, while you watch this. And without it, the device in your hand would not exist, nor would any modern computer. Not one, anywhere. Somebody built a machine to do this. It cost decades and billions. To understand why, we go back 30 years. A microchip is not assembled. Nobody places those structures by hand. They are drawn with light, all at once, onto silicon. Light shines through a patterned mask, and optics shrink it down. It prints onto the wafer, then again, layer on layer. For decades, this got easier, every single year. The answer never changed. It was always the same. Use a finer brush. A finer brush means shorter light. Then the industry hit a wavelength of 193 nanometers and stopped. Engineers kept printing smaller with tricks. Every trick made chips slower and more expensive. Time was running out. There was an obvious answer, and everyone knew it. Go far shorter, down to 13.5 nanometers. That is called extreme ultraviolet. It is 14 times shorter than what the industry used, and it has one catch. Extreme ultraviolet is absorbed by everything it meets, not by some materials only, by every single thing it touches. It is absorbed by glass, which means every lens ever built for this work was suddenly useless, all of them. It is also absorbed by air, not by smoke or dust, by ordinary air within a few centimeters. So the entire light path must be a vacuum. Every lens must become a mirror. The whole design changes. Except ordinary mirrors do not reflect this light either. What works is a stack, alternating layers of molybdenum and silicon. Get the thicknesses exactly right, and the layers reinforce each other. Get them slightly wrong, and you have a black surface. Those mirrors are made in southern Germany. The town is called Oberkochen. It has about 8,000 inhabitants. The company there has worked on optics for this single purpose for roughly 3 decades. Not on optics generally, on this. Picture one single mirror sitting inside a polishing machine. Not for days, for months of continuous, measured correction. The requirement they had to meet sounds invented. It is not. The surface may not deviate by more than a couple of atoms. Here is what that actually means. Take one of these mirrors, enlarge it until it covers the whole of Germany. On that surface, from the North Sea to the Alps, the tallest bump would be 1/10 of a millimeter. That is the standard. For the newest generation, it is tighter still. Scale the mirror up to the size of the Earth, the whole planet. The largest bump anywhere on that planet would be as thick as a playing card. That is the tolerance they hold. As far as anyone can tell, these are the smoothest objects human beings have ever made. Anywhere. Ever. And even a mirror that perfect returns only about 70% of the light. 30% is lost. At every single bounce. The light bounces off several of them in a row. Losses multiply at each one. By the end, most of it is simply gone. Which brings us back to the droplet. Think about the maths. If most of your light dies on the way, you need an absurd amount. There is no lamp that produces extreme ultraviolet. You cannot buy this light anywhere. You have to create it violently. The method works like this. Drop molten tin through a chamber. Shoot each falling droplet with a carbon dioxide laser. But not once, twice. The first pulse does not vaporize the droplet at all. It flattens it into a disk. A flat disk catches far more of the second pulse than a sphere ever could. That is the whole point. Then the main pulse arrives. The tin becomes plasma. It burns hot enough to radiate at exactly the wavelength those mirrors were built to reflect. Drop, flatten, vaporize. That entire sequence repeats 50,000 times in every single second of operation. And it must keep going for months without stopping, without missing, and without coating those perfect mirrors in tin. If one droplet drifts by a fraction, the laser misses it. The tin sprays instead of vaporizing onto those mirrors. Getting that stable took years on its own. Years. For a long stretch, the light source was the reason the whole thing failed. And one part is still being studied today. What exactly that droplet does in the microseconds it is struck, nobody fully knows. Work on this began in 1997. A consortium of chip makers funded it. So did 3 American national laboratories. The first working machine shipped in 2010. Count that out. 13 years from starting the work to the first delivery. 13 years on a technology that might simply have failed. Nobody could promise it would ever print a chip. Nobody knew. By 2012, the development cost more than the company could pay, more than its own revenue could carry, far more. Picture that board meeting. You are asked to hand over billions for a machine nobody has yet seen working. So, something unusual happened. The 3 biggest customers stepped in. They bought a stake in their own supplier. Intel, TSMC, and Samsung took 23% together. The price was 3.85 billion euros, paid jointly. On top of that, they committed well over $1 billion more. Not for shares this time, purely for the research program. Read that again. The customers had to finance their own supplier. Otherwise, the machine would simply not exist today. Estimating the total cost is hard. Public research, consortium money, and company budgets ran together for 40 years. What is not in doubt is the outcome. One machine, one supplier, and no second source anywhere on the planet. Today, that company holds the entire market for these machines. Not most of it, all of it, worldwide. It ships a few dozen of them per year, not a few thousand, not even a few hundred, a few dozen, worldwide. Each one weighs roughly 150 tons. It is about the size of a bus. It travels in dozens of containers. Reported weights vary by model and configuration. That tells you something by itself. These are not standard products. Around 100,000 parts, 2 kilometers of cable and hose. It arrives in pieces and is assembled on site. Every advanced chip on Earth passes through one of these. Every phone and every data center, every AI model you use. There is no workaround here. You cannot buy a substitute anywhere, and you cannot build one quickly, at any price. Not because anyone hides it. The physics is published openly. The problem is doing it for 30 years without stopping. The device you are watching this on exists for one reason. A droplet of tin gets hit twice, 50,000 times a second. If you want the next one, subscribe, and tell me in the comments below, which system should I open up next? I read them all.